So let's get started. So far, what we did was we tried to do basic amount of computation using an RDD. Like in the last time, what we did was we computed the standard deviation. We computed the standard deviation on numbers using the, all right. So the slides are same as the previous one. So there's nothing new. And you can use the same slides. The project, yes, a good question, Vinta. So last time we discussed about how do we process the binary files. So I have included that. And when we talk about key-value pairs, so there is one more concept that I want to talk about called key-value pair RDD before we start with the project. All right, because invariably all the projects and all the works will involve processing the values by the way of key value. Therefore, it will be better that we discuss that. So I've actually done that part. So what we will do is we will do the processing of binary files. We will, let's say you have zipped files and you want to unzip them or decompress them, then you can use Spark. Also, all right. So we will be discussing the project. I think it'll be wise to do that time. Okay. And we will do that together. All right. So a question from Binta is, you may spot the project in advance for our preparing for it. Yeah. So I think the easier one will be to actually. Okay, actually, don't worry. So I think it's not too far. So let me just move ahead with key value, and then we can start discussing the project. Don't worry. All right. Yes. After today's class, you will be ready for doing the project. So, okay. So there are two things I'm thinking of handling with binary data. One is converting the zipped data into the JSON objects. And second project I'm thinking of is taking images and resizing them and saving them. Let's say there are profile pictures and we would like to convert them from colored into black and white on a massive scale. So we can experiment that. All right. Or maybe what I'm also thinking is that let's say there are some images and we have already built some program to recognize something in the images. Can we launch that program using our standard MapReduce RDD in order to do the image recognition on a large scale? All right. So those kind of things I'm thinking, and we can start that after key value RDD. All right. So yeah, those are far more practical. The general strategy is that even if you're training that, let's say in industry there is a machine learning is going on. Let's say people are training their models on various kinds of data, right? Either that would happen through MLlib, Spark MLlib, or even if that happened by somebody, we should be able to call those program or run those program using our Spark. So we'll learn that part, right? So let me just after today's session, we should be able to handle the key value and hence a couple of projects. All right, great. So let me just get started. All right. So far what we have done is just learned how to do basic amount of computation. We did the computation of standard deviation. Now, second one is second question to all of you is, let us say we have to pick approximately some percentage, not exactly. So the objective of this exercise is to pick a random sample from a huge data. Imagine you have huge number of text lines in the input. And what you want is you want to pick random sample lines from that text file, right? Random sample lines. So, and you want to say that, okay, I'm looking for 5% of the data, or I'm looking for, say, approximately 10% of the data. So how will you do that? So we want to pick random sample from the input data using whatever we have learned so far. We have learned map, we have learned reduce, we have learned filter, we have learned map, flat map, and so on. So my question to all of you is that how will you solve this? Imagine you have input data and you have to write a function called sample, and that one takes an RDD, and this basically also it one takes this function that you're trying to design. It takes an RDD as argument, and it takes the fraction of the sample, fraction of the total data that you want in the sample, and it should give you another. It should basically give you a local array of the data. What will you do? Okay. Question from Mohammed is call flat map and generate a random number counter. Okay. Let me give you one more example. Okay. Let me just open the Jupyter notebook. Okay. I think that'll, or I'll just open, I like the Spark shell. So I'm just going to go with the Spark shell. All right. Because Spark shell gives me a little bit more detailed approach than the notebook. A notebook is not yet very stable. So here, let's say we go to terminal. All right. We go to terminal and we say spark dash shell. All right. Whatever we are learning is going to be same in Spark 2 and Spark 1. So I'm just going with default Spark 1. All right. Okay. So let's say we have var RDD equals to sc dot parallelize 1 to 100, right? Let's say this is the RDD we have. Okay. This is the RDD we have. Okay. All right. Good question from Bintao. Let me just finish that part. All right. Now we have just created an RDD with 100 numbers, and what we are trying to do, we are trying to find a sample of the data. So if you take a look at this RDD and we say take 10, it'll give us first 10 numbers. What we want is a fraction of the total records. Or let's say we want to out of 100 records, what we want to pick, like 5% of the record which are random. How will you do that? Suggestion from Mohammed was that call flat map and generate the random number counter. Okay, I would love to understand more, Mohammed. Anybody else? So how will we?
Just to add on what I was saying is, if you call flat map, everything is like a huge array, right?
Right.
All the numbers are in the form of an array, and then in Python you have a package called as random. I think the name is random, and then to that you pick up the samples from that array.
So my question. Okay. So what will flat map give you?
So if my array will be like one huge array, instead of multiple arrays, I'll just have one array containing all the values. From that array,
yeah. So right now also this RDD is your one single array only, right?
Correct. So here you don't need to call the flat map. Here it's fine.
So these are basically 100 numbers. Now, what do you want to do?
You use the package from Python.
Okay.
It's called, I think, import random.
Okay. Import random. Okay. Let's say
Uh,
you have random.random function, correct?
yeah, I think that's the function.
What does it generate?
I'm not sure of what it
Okay.
takes. I think it takes a couple of parameters.
Yeah. Let's just
The
assume
seed
some
value
function.
and the
Yeah.
seed value and
So it gives us, let's say, so you are saying, imagine that we have a random number generator, right?
correct.
Okay. And it returns us, what does it return? Let's say a number, right?
Yeah, each time it returns a number.
Let's say it is returning a decimal number. Now,
No, it will not return a decimal number.
then
It will just return an integer,
integer between,
0 to 100.
okay, let's say we pass 100 here and it's returning a random integer. Now,
So each time supposing this number is an index, so you go to that particular index and that then get the value from your RDD.
okay, so are you saying that, let's say we are looking for X percentage, right? We are looking for sample size as sample size as say 0.1, meaning 10%, right?
10%. So 10 values. So you run your
10.
counter for 10 times.
So, okay, so, okay. So can you mute, please? Yeah. RDD dot take, right? And how will you just maintain this one? Okay. So something of this sort, right? For,
Yes.
right? For sequence in sample size multiplied by RDD dot count. Okay. This is what you're suggesting.
Yes. Yes.
Okay. Now, do you notice how many calls are we going to make to the, how many jobs are we going to execute for this?
Yeah, 10. The number of
So if we say like 9, so this is going to actually do 90 jobs,
correct. Each time you go to the RDD.
right?
So too
Right,
much IO, right?
right, right. Now, good, very good approach. I mean, for first timer, at least we have some approach to compare with. Okay. Now, anybody else who wants to give the input? A question from Alok is, we can use a filter or map or flat map. Okay. And all right, those who have joined late, I'll reiterate what we are trying to do. What we are trying to do is we are trying to generate a random sample from given RDD. Imagine that we have an RDD and we want to pick a random sample. Okay, is my voice not audible, or because Shravanti is not able to hear? Everyone is able to hear.
Sandeep, I have another
Yeah,
suggestion on this. Can you
yeah.
not do partitions like, see, supposing you want 10 samples. So you divide the data, the parallelize into 10 partitions, and
Right,
then
right.
do selection once from each partition if you want to
Okay,
get values.
okay. So are you saying that if it has, let's say, you're saying comma 1, right? Let's say it
Comma
has 1.
10. This would be one partition, right?
Hmm.
No, so if you want to pick up 10 partitions, so
Okay.
I mean 10 values, you
Hmm.
divide the data set into 10 partitions, and
Okay.
then you pick an element from each partition.
Okay. Okay. So
So
are you
you have
saying,
a sample from each partition.
okay, but see, the thing here is that sample size is user input. Okay.
Mhm. Right, right.
Sometimes you want to do zero point 0.1 sample size. Sometimes you want to do 0.2, 0.3, 0.0, 0.01, that kind of.
So it's
So
dynamic.
dynamic, correct. So we are trying to write a function which gives us a random sample from huge data. And finding the random sample is very common. The one important thing that we all miss in case of sampling is sampling doesn't have to be exactly zero point 0.9, right? It doesn't have to be exactly like 90 records. It can be 89, 87, or 91 or 92. Approximately, statistically, the sample size should be approximately 0.9. Okay, this is a very important bit.
Your sample size 0.9 means you want 90% of your data.
Yes.
90% of your data.
Right. Sometimes I might want 0.01%, that is 1% of my data, right? And sometimes I want, so this is a user input. I'm just giving an example. Okay.
Sandeep, I have a
For,
question here.
yes, go ahead, please.
You said we need to get like 70 or 80% of the data, right? So within the for loop, why are we passing this random number of 100? Because we are selecting the data from an existing data. In that case, how
So
will
this,
the
yeah,
proceed?
this is an approach by Mohammed. Like I'll just
Okay.
write. Okay.
Okay. Yeah. Okay. I mean,
Okay.
I want to know in real time how it will be.
Yeah, I want to I see right now we are seeking the inputs from all of you. So
Mm-hmm.
imagine that you have to, I'll just save it. Okay. April BDHS. Right. This is important. So you please come up with the approach. So, so your question was, why are we passing this, right? Why are we generating random number?
Yes, that is my
So,
question.
so his approach, at least at least we have one approach right now. His approach is that whatever sample size you are looking for, first find out how many counts are you looking for. For those many times, all you do is you take data at that position. Although this is wrong because you can't access exactly at the can't access exactly at that point, right?
Correct.
Okay, so that's another exact index. For that, again, we'll have to do another set of things that we'll discuss later. Okay. Any other suggestions? So one is there are multiple things here. This is important part. Important part. So what we are trying to do, is we are trying to do approximate, not exact. Approx. Okay, not exact, say right, point zero 0.01 fraction, right? If let's say there were 1,000 records and we were looking for 10 records, it might give 9 or it might give us more. Okay, so this is a important bit. So anybody else? So what we're trying to do, we have an RDD, we want to take sample out of it. Okay, we want to take sample out of it. Binta, you remember our earlier discussion? Can we apply the similar technique that we studied earlier? Anybody? Like dropout? Okay. Filter, yes. So, okay, Alok says filter. How do we do that? Go ahead. Okay. Okay. What is it that we are trying to do is what we are trying to do is we are trying to do is find the random sample from the data. So my question to you is, how do we come up with the approach so that we can pick the random sample from a huge RDD? because your data would generally be really huge and you would just want to pick certain records and certain sample size. So sample size is something we want the input from the user and should be dynamic. And your approach has to be efficient. Okay, okay. So Alok's suggestion is that, okay, we have a good suggestion from Hitendra. And question from Alok is that we can use filter, we just discard which we don't want. How do we discard which we don't want? How do we choose which one to keep? A question from Hitendra is generate random number and apply the filter of desired number of records from that number of filter. Okay. 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 Give me a little bit more details. Okay. A question from Grishma is, I feel the filter gives flexibility of selecting desired set. Okay. So yeah, filter basically gives us a way to pick up a record, right? But we want to pick the, okay. Okay. I want to pick a fixed sample, some sample size. Okay, from this. If I can say less than 500 only I want. Okay, no. So what we are looking for, we are looking for a subset of this one. We're looking for a subset of this one, and such that we should be able to pick that. So although there is already a function called sample, right? So this sample will, okay. Okay. So let's say it has two methods. All right. So I'll show you. And here I'm saying give me 0.1. That is, give me random one record. Okay. See? Oh, this is all right. So every time it is giving us random 10 records. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it has 13 records it has given us. Okay. And this is an important bit. So there is already a function called sample, which gives us sometimes 8, sometimes 13. Though we have, it is supposed to give 10 records. This is exactly what I meant to say, that it should give us, so this is what we want to build by ourselves. Okay.
Sachin, I have a Sandeep, sorry.
Yeah. Okay.
I have a question over here.
Yeah.
I see the return value is sorted. So does it have something to do with being sorted? The data has to be sorted.
Not really. Actually, the input data was sorted, so we are getting in the sorted.
Correct. But does sorting play a role over here?
Not really. Not really. Because sorting will become too heavy, right? So the data input data was sorted, so we got the we got the result. So yes. So Alok and Hitendra, your approach looks interesting to me. Looks very relevant. Why don't you give me a little bit more details? I see. Okay. I think Alok got it. I think Hitendra also meant a similar thing. Okay. So David's question is, if random, then why numbers are increasing? Because our RDD, right? Our RDD had increasing numbers. We just took 1 to 100. That's why when it is picking, it's picking in the same order. All right. It's not shuffling them. If our input data was unordered, it could have given us unordered records. Okay, good. It's not picking, yeah, correct. That's right. It's not picking numbers. It's just generating number. It's not generating numbers. It's just picking from RDD. So this, when we are saying RDD, this is our RDD that we created earlier. I think before you joined. So we had created an RDD like this. Okay, we had created an RDD like this. And we said, don't replace, as in don't give out the same record again. and give me 0.1. So we want to design a similar function which could give us a percentage. All right, great. So yes, that's the way we would go look. Great. False is without replacement, right? It should not repeat the numbers. If we say true here, it'll start replacing. It'll start giving the same numbers again. You can see 9 has been repeated twice, 41 again, 40 again, and so on. Okay, so without replacement is what we are looking for. All right, so great. So yeah, history, yes. Okay, so this is all right. This is my previous work from here till here. All right, great. So what we did was we tried to do was we tried to find out the sample, random sample from the data, and I think the approach from Alok is correct. So the one approach was that we could have actually just generated a random number and accessed a particular index. We could have just accessed a particular index, and we keep on doing it again and again until we get the desired number of outcomes. But that will be just too much of work, even though that approach will give us exact sample size, but it would not be performant, because every time we are going with this kind of approach, so if we're going to go to the RDD, take it, and whenever we execute take, it's going to take time. So therefore we need to come up with a far more efficient approach. So it's actually a pretty simple approach. It's just little twisted, and this not how we generally think. Therefore we are able to think about for loops so easily, but it takes a while to get used to maps and filters. All right, that's why it takes some time to even get used to SQLs. So whenever you think about parallelism, you should think like the way people who write SQL query do, right? They think of data as a set. Instead of thinking as a for loop, we always think as what kind of filter can I apply? What kind of joins can I do? So that way. Okay, so when we are thinking in terms of RDD or any parallelism, you must think like SQL, like think in terms of SQL, or think it's like the SQL engineers, DBAs. Okay, so let me explain the solution. Imagine that for time being, let's just say that we are looking for picking up 50% of the record, like half of the records, not all of the records. Okay, so today morning we discussed something in the deep learning session, that we have a technique called dropout in neural networks, where we pick 50% of the data, 50% of the neural network. So how does it happen? So coming back to here, Shravanti, you are unmuted, right? So in the same way, let's say we want to just pick 50% of the records, not the entire one. So it's quite useful and quite common to pick sample, by the way. It's really common. And it's a very practical question. So the approach is very simple. The approach is very simple. We pick a record from RDD and do a coin toss. We pick a record from RDD and do a coin toss. So how do we pick? So the way we do is use the filter, and in the filter we say that, okay, do the coin toss. If it's head, keep the elements, otherwise discard it. Okay, this can be achieved easily with the filter. So for picking any fraction, we might use a coin with having, say, hundreds of faces. In other words, we could use a random number generator. As Mohammed suggested, we could use a random number generator to pick a fraction and see if it is lesser than our fraction that we're looking for. All right, so please notice that this would not give the sample of exact size. It would give sample of approximately the same size as we are requesting, but not exact. So all we do is, against every record, we do the coin toss. So we do 100 coin tosses. And if it is head, we retain it. If it is tail, we don't retain it. So why it is right? Why it is efficient? Because this coin toss will happen parallelly on multiple machines. Therefore, and coin toss does not take much time. Okay, it is the transport of the data that takes more time than generating the random number. Imagine that we are looking for 0.1 fraction. So we define a function called coin toss, and what it does is it calls Scalar's random function, which gives us the random float. If this random float is lesser than the fraction that we are looking for, then it returns true. Otherwise, it returns false. Okay, so it basically is doing the coin toss for us. It's saying that okay, it is head. Let's pick the uh, element. Imagine that we had to pick 1 out of 6, and we were having a dice. So what we'll do is, okay, throw the dice. If it is 1, then pick one of that, right? So it's the same thing that we are doing here. Okay, so let me put it again. Imagine that we had to pick 1/6 of the total records. Okay, we had to pick 1/6 of the total records. So what will we do? We will, against every record, we will execute the random function. If, or we will execute we will throw the dice against everybody's name. If the dice says 1, then we keep it, otherwise discard it. So that way we will get exactly same fraction, same almost like 1/6 of the total records. All right, and then we apply this function as a filter, and once we are done with that, we do the collect and then print. Okay.
Sandeep, I did not understand you.
Okay, let me do it again. So
I mean, the fraction I did not get. As you said, 1/6 of the collection means if the dice turns 1, then we are selecting that number. Why are we saying if it is less than or equal to fraction?
yeah.
Second and third step.
Okay, so although you are clear that if we do a coin toss, you'll be okay.
Yes, that I got it, because we'll be selecting any number which returns 1, right?
Right. So, okay, let me break it down into multiple steps. Okay. So imagine we had to pick only 50%, okay, for time being. And we have this coin toss. And what we are doing in the coin toss, we are saying, so what it returns true. So we'll say if throw underscore coin equals head, I'm just writing a very arbitrary code, then return true, else return false. This is clear to everybody? Imagine that we were basically, let me just change its name, should retain. Okay, should retain. Well, let's say this is the function, and yes. So so we have an RDD with these numbers, and we are looking for, say, 50% of the records. Okay, so we are throwing a coin. If the throw of the coin gave us head, then we are retaining it. Otherwise, we are discarding it. All right. Is this pseudocode okay? This is pseudocode. This won't work, right? So imagine that we want to pick 50%. So then if that is there, then you're convinced that this code will work, right?
But not all the times it can turn head, right? I mean, if 80% of the time it will be head, then we won't get 50% of the
So yeah, if the coin is biased, then then there will be a problem. If the coin is not biased, if we are throwing it 50 times, we are throwing it 100 times.
100 times.
So we'll get 50 times of head and 50 times tail.
But there is no guarantee that
There's no guarantee. Yes.
That was
Exactly.
yeah.
If they, since there is no guarantee, therefore the outcome might have more or less 50% of the records.
Yes. Yeah.
Okay.
Okay. Yeah. But I did not get in it. I mean, the previous example.
Yeah, yeah. Previous, I'll go back after this.
Okay. Okay, I got it.
Okay. So is this clear to all? Will this work? So we are saying, though the fraction is not being used, okay.
So Sandeep, this will not collect 50% of the data because we don't know how many times head will come and how many times tail will come.
Okay. Approximately how many times will it come?
Yeah, 50%.
50%, right? It might come 52, 53. That's why even if you use the library function, it won't give you exact 50 records. Sometimes it'll give you 51, 53, 50, 49. And that's why I had specified in the beginning that we are looking for approximate, not exact.
Okay.
Okay.
So this will approximately return 50%.
Yes, yes. Good question. All right. Will it work from your perspective? From your expectations, do you think it's going to work? All right, great, great. So it will work. All it is going to do is this one is going to return true or false. It's going to return true 50% of the time, false 50% of the time. Also notice that we are not using the X that is being passed here. Okay, so we're just throwing a coin and we are depending upon the luck. Okay, so we are not depending upon the parameters here. So we are saying that should retain or not. So this function is going to be executed 1,000 times because here, in this case, the records are 1,000, and in case, so approximately 500 times it's going to return true, and 500 times it's going to return false, and that too randomly. Therefore, 500 out of this, 500 records are going to be retained. All right. So this was a really, really simple one where we just wanted where we wanted a number of records. Now imagine that we have we want to get, say, 10%, right? We want to get 10% of the records. So what will we do? We will throw a coin, throw a dice, throw dice with 100 faces, 10 faces, okay? And in case the face is, say, 1, then we say true. Is this okay? Will this be working fine for 10%? For 10%? If you want to pick 10% out of it. So we are saying throw a dice which has 10 faces. In case the face value is 1, then move ahead. Otherwise drop it. So 1 out of 10, it will keep. 9 out of 10, it will drop. Okay, because this function should retain is going to be called against every record. All right. Now, so so in the same way, what we are going to do is, instead of throwing a dice, instead of throwing the dice, okay. All right. Is there anybody else who wants to record? Okay. All right. So I hope this is clear. Now, let's say, right? Now, what we are trying to do is, let's say, we don't have this function like this. Instead, we have another kind of function. We have the function like this. Okay. We have a scalar function. Okay. Which returns us a decimal number, which returns us a number between 0 and 1. This function from scalar actually returns a random number between 0 and 1. I'll show you what does it do. Okay, so every time you run this function, you get a decimal number. Now, This is between 0 and 1. It's going to give us a number between 0 and 1. So what is the probability of getting 0.2 out of this? Very low, right? But what is the probability of getting numbers between 0 to 0.1, right? What are the chances of getting numbers between 0 and 1? 0 and 0.1. Yeah? What are the chances? Sorry, not changes, chances. 10%, right? Okay. And what are the chances of getting numbers lesser than 0.5? 50%, right? And what are the chances of getting numbers lesser than 0.6? 60%, right? Therefore, what we do is we basically compare if, right? Oh, this is wrong. Okay, this I have done wrong. I'll just fix it again. Yeah. So, all right. So this is exactly what we are doing. So we are saying throw the dice, return true if it is lesser than fraction. Okay. So if we are looking for, say, 60% record, so all we have to do is throw the dice and check if the numbers are lesser than 0.6. Okay. Now it makes sense to you? So whatever fraction you're looking for, let's say looking for 10%, just check if the value is less than that. Okay. All right. A question from Grishma is, in real time, when do we need this? Honestly, you don't need to create such kind of function, right? But the value of finding a sample is very important. So whenever you have big data and you want to just take a look at the holistic way, whenever you are testing your MapReduce, when you're testing your program, you would like to run on a small subset of a bigger data. So instead of just picking first few records, you would always pick a sample of it, a random sample of it, based on how much your local machine can support. So you'll just generally pick random sample from a bigger data, huge data, like few terabytes of data, and then you will do the local computation using the sample, right? Because sample is something we can look at and tackle. We can't look at the whole data at one go. So sample is very important. The question is, why do we have to write our own sample, right? Why? Because the reason why I've included this example is that it's very common to have such kind of scenarios, and a lot of number of times we kind of think still in terms of our for loops. Okay, therefore we have to start thinking the SQL way or set based way in order to solve such problems. And almost every machine learning application has such kind of method to pick the sample. That's right. Thank you, Maman. All right. So good question. So moving ahead, so we were able to define this. So I can show you, this is actually pretty simple and it would work. I'll just give you all of you the code.
One quick question over here. So the random sample function, which is inbuilt, works in the same fashion?
Random sample function.
You showed the inbuilt sample function, right?
Yes, it works in the same way.
A similar fashion.
Yes.
All right. That's why the sample size is not the same each time.
Exactly.
Thank you so much.
But they have, I'm not sure because they have a similar strategy, statistical strategy, and there are actually there are multiple ways of generating sample. This one is the easiest one, and for that matter, just generating the random sample is such a hard problem. You will realize later. Okay, so there's an algorithm from DENUT. So those who don't know DENUT, and he is the kind of god when it comes to the computer science. There are many algorithms after his name, and so one of the algorithm given by him is based on just very simple finding the random sample, and that's kind of de facto. So my approach in this is based on similar one as Nuth, but I have avoided getting into the complexities. All right, great. So
Sandeep, this is also random. Scalar.util.random. This is also random number provided by Scalar.
yes, but it gives us a fraction between 0 to 1. And what we wanted was, we wanted to pick random number of records from an RDD. Okay. So we want to say, give me a sample of a bigger RDD. Okay. Let's say we have terabytes of data. We want like 1 MB of data, 1 MB of records, which are random samples. Okay.
That's why we pass in filter function.
That's right.
Yeah.
Okay, so there are quite a few algorithms around it. I've just written the most simple one. It may not be giving us exact number of values. Okay, there's always a complexity around finding the random, but this one is actually simple as well as good enough approach. All right, so and I'm sure that okay, so I'm sure that in the interviews you will be asked similar questions if you're going for say Spark developer position. Then you should be kind of ready with these kind of answers, right?
I was talking about the solution. You remember about partitioning the data set into those many parts,
Right.
as the number of percentage, and then picking a sample from that partition. How does that? Will that be okay?
No, that will be not okay because that will be biased because it will only pick from only one partition, right?
No, no, no. What I'm saying is, if say supposing I want 10 values
Okay.
from a set of 100, so I divide the data set into 10 partitions, and then my sample picks up a value from picks a value from each partition.
Okay.
The number of from each partition I pick up one, so in the end I have 10 values.
Right, right. But cost of repartitioning is too hard, right?
Okay, partitioning is an expensive operation.
Yes, because it would move from one place to another. Okay, good question. Good question. All right. Now, a question from Binta is, for some functions, it is with brackets and some without. Okay. In Scalar, sometimes you don't need to give, you can actually skip the brackets. It is little weird for me. I'm not used to not using the brackets. I'm quite used to using the brackets. So actually, I'll show you what it means. Okay, this is something I was thinking of talking about. So let's say we did define a function called coin toss, right? We defined a function called coin toss, right? If I call coin toss just like this, it's saying that apply a function, apply argument. So okay, let me just show you. Okay, so okay. So coin toss basically takes an integer and we are calling it that way. It gives us true or false. Okay. And all right. So for some reason, yeah, this is a little weird. Sometimes you may provide brackets. Sometimes you may not provide brackets. That's why I am not very comfortable with say these methods. So for example, let's say RDD, right? RDD.count. Either we can call it like a function or without the arguments. So I think you need to define it that way. All right. So many methods can be called without the brackets. Okay. Like for example, like here, let me see if I could call something like here. I could skip the brackets probably and then see how it works. Okay. Okay. So sometimes it needs brackets, sometimes it not. So I prefer using brackets all the time. Okay. So that is little crazy with respect to the scalar. Maybe I'm not quite used to that. So sometimes it wants to put the brackets and sometimes you can skip. But as a general thing where things work perfectly fine, you just put brackets. Okay. Because that I'm quite comfortable doing in Python, doing in Java, doing in C, doing C Sharp and C++. All right. Though they have come up with the idea that let's skip the brackets if it's not required. Right. So yeah, that's another problem, Bintao. So sometimes it is an attribute and it doesn't take an argument. So length is an attribute. It's not a function. So yeah, that's unnecessary complexity, and probably they will have to avoid this. So here the length is an attribute. So I would say that let's stick to the thumb rule. If it's a function, we put brackets, and if it's not function, like if it's an attribute, then we don't need to put brackets. All right. So you will generally see that in detail.
I have a question on the code.
Right.
Why does the function cointoss take a parameter x?
Yeah. So that's a standard definition of a function that filter requires. Filter wants you to take some argument, same as what is the data type of RDD. All right.
But here we are not making use of the parameter
Exactly.
anywhere in the function.
Exactly.
So you cannot have an empty parenthesis. You have to have something that goes into the function.
Correct. Same as the data type of the original RDD.
Okay, yeah, right.
Okay. Yeah.
Good.
All right. A question from Binta is, for some function which has itself parameters, it need a parenthesis. So class has attributes and methods. For methods, we are going to use the parenthesis, and for the attributes like a variable, we are going to not use the parenthesis. All right, just like in every other language.
Sandeep, this sc.pella is not giving me array. It is giving me
RDD.
Yes.
That's right.
You, it was giving some array.
No, it is not. So I was actually calling it so. Okay, so you can see. You can see that?
Yeah.
Okay. All right. So I hope this is clear to everyone. Any questions on this?
Sandeep, I have a question again here on the third line.
Mm-hmm.
You said we need to pass some like integer value to the count as function.
Yeah.
What exactly will we be getting from this?
We have to. It will be this function coin toss.
Hmm.
This function is going to be executed against every value of this RDD, right?
How will how can we confirm that it will execute across all the numbers, because nowhere we are passing
Good
the
question.
RDD parameter. I mean, RDD value.
What?
We are nowhere to the counters function we are passing RDD variable.
Yeah. That's how it is. So on RDD, we are calling this function. We are saying RDD dot filter, and then we are saying coin toss. So
Okay.
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 Yeah. All right. Great. So I think, yeah. Question from David is the code from previous example actually is the same one that we discussed. Okay. Earlier I had given you the same code. Okay, so yeah, this is the same code. All right, moving ahead, and yeah, this is the first code we used. Another question is entire RDD will be evaluated. That's correct, Hitendra? Okay, yeah, I have executed Sachin the code, and let me just show you the local sample example. So I have done my RDD here. Now on my RDD, I could just say take and or say collect. Okay, so my RDD will contain the sample, and here whatever fraction was it there. I'll show you again. Okay, so let me just copy paste it again. Yeah, here we go. So what we have done is this part, this local sample is what is there. So every time we are going to execute this, it is going to give us some amount of records. Okay, so we are saying 0.1, that is 10% of 10,000 records. That is going to be right, going to be around 100. So you can see every time we gather the local sample, it's approximately 100, not 100. All right. So is it mandatory to pass argument in the function which is going to? Yes. We need to define exactly that way. So the definition of this coin toss, the definition of this coin toss does not take any other argument, right? You have to use some kind of global variables. We'll talk about how to handle the global variables in future. All right. So yes, if you do not pass, what will happen? It'll throw an error. Okay. So try that. All right. So that was our basics of RDD. I'm going to walk you through a couple of more transformations quickly, and that would help you understand the more operations on an RDD. All right. So RDD has an inbuilt function called sample, the one that we just designed. It also has the same function. The first argument is with replacement, meaning the elements will be repeated. So whatever it picks in the first one, it would do the same again. And if with replacement is true or false. Okay. Next is all right. So with replacement is a little harder to implement. Without replacement is easier the way we did. So basically works pretty seamless. So it gives you the entire sample, and very easily. You don't have to write any code. All right. Next is mapPartitions. mapPartitions takes a function. mapPartition takes a function as an argument and executes that function on every partition, not every record, every partition. All right. So you will get an iterator to the records. Okay. In this function, whatever mapPartition takes, it'll give you a small array or iterator to an array which you have to apply. So if you are writing a function, say f, it should take an iterator of the same data type as the input values. And this one needs to go over the list. Why? So mapPartition executes your function on a partition. What does it mean? It means that the partition is going to have many elements, and your function will be called on these many elements. Now, if it was providing the whole array as in memory, then it would be inefficient. Therefore, instead of giving your function the whole array, it gives you kind of a cursor or kind of an iterator to the partition. All right. All right. So let me give you the slides. The slides are generally available there. Okay, let me just give you. All right, so this is what happens. All right, so we're defining a function which is operating on iterator, and it can give an iterator back. Here we are just giving the iterator to the list, and it is operating. So if let's say this partition, how many partition will this array has? So this will sc.parallelize will create an array containing elements from 1 to 50, right? And it'll create 3 partitions, and in this three partitions, on these 3 partitions, your function will be called. Now your function is operating on all the elements per partition, therefore it will return the summation of each partition. Okay, so it will return a summation of each partition. All right, is it making sense to you? So mapPartition is another transformation. mapPartition is another transformation, just like map. In map, your function was executed against every element. Here, your function will be executed against every partition. Question is, why would I use mapPartition over usual map? In case of usual map, the usual map is great if it is not required to operate on a partition. But let us say that you are saving the RDD. Let's say you want to write an RDD into a database, right? And what do we do when we talk about database? We open a connection, we write the data, then we close the connection, right? So every time opening a connection and closing the connection in every map function would be very, very inefficient. Therefore, if we are using mapPartition, what we could do is we could operate on each partition and open the connection in the beginning of the function and then close the connection in the last. So that makes it extremely fast. Okay, so you'll only have to open 3 connections. So those are the examples of where mapPartition could be used. So whenever you want to operate on many elements together, because operating on many elements could be faster, in those cases you use mapPartitions. All right. The next function is the next transformation that is given to you is sortBy. Okay. SortBy. Let me again go over this example. This example is more involving. So here, let me just talk about. Okay, so let me give you. Okay, so here what we are trying to do is. Okay, so here what we are trying to do is we are creating an RDD. Okay, then we are defining this function. What it does is it returns the sum. It returns the sum of any iterator that we want, any iterator. Okay, so let's say I am saying f of 1 to 10. Will it work? Okay, it says that it requires that. So I could say list here, list, and we could say iterator. Okay, why does it say that? Okay, let me just, okay, here. So list, say where L equals list, and I say 1 to 10, L dot iterator. Okay, so L dot iterator is what we have. I see.
I think it is
Okay.
expecting you to pass some value to the
Yeah,
iterator.
yeah, yeah, yeah. It's expecting me to pass something. Anyway, forget it. So basically, it's asking me to pass an iterator for something else while it is something else. Never mind. So we are not basically called directly. We are not able to call app directly, but we are able to call it on our RDD. Okay, so don't worry about this. So we are able to create a function f. Now we can call this function on our, let me define a new output equals this. So we are calling this f function on the partitions of RDD, right? So this output, if you say take 10 or take say 3, because there were 3 partitions, we get the results. Okay, we get the results, or we just say collect to see what's there. So you can see. So here essentially what we are doing is we are going over the input, going over the so here going over each partition, executing your function, and whatever is the result, it is gathering here. That's what it is doing. All right. On the similar line, also there was a question regarding next here. So here, the way you iterate over an iterator is using this kind of a syntax. You say, while this condition is true, then sum equals sum plus some value, right? We are incrementing from the next. Okay, so this next gives you that particular value. Okay, so let me give you the result.
I have a question on this one.
Okay.
Um, when you call the parallelize function using the second parameter, which is 3, it divides the data set into 3 partitions, right?
Yeah,
So it like for the first partition will be the division of will be the first part of the data set, or it's going to be like random sampling again over here.
it'll be sequential.
Or sequential sampling of the
Yeah,
data set. That's why the answer is the same each time.
correct, correct.
Okay, thanks.
Good question, good observation. All right. Now, similarly, there's a very powerful function called sortBy. SortBy takes a function instead of just sorting by numeric value or something. It takes from you a function that basically decides or compares 2 elements, and using that function, it sorts the data. All right. So this also takes the argument like ascending equals to true and number of partitions. How many? What is number of partition? In the resulting RDD, how many partitions do you want? Okay. So all you need to do is you need to pass a function that is used for computing the key on the basis of which sorting will happen, right? SortBy doesn't give you the luxury of comparing 2 elements. Instead, it gives you the luxury of defining a function which converts the input data into a key on the basis of which the comparisons will happen internally. Okay. So, all right. There's a question from the previous one from Bintao. How does i.next work? i.next is basically giving you the next element from the iterator. So this is how generally the iterators work. If you have seen something called cursor, what we do is we get a handle to the beginning of the data. Then we say if it has next, then give me the next. Otherwise, we stop iterating. Okay, that's how most of the iterator pattern works. So we say while I dot has next, then give me the next, add it to summation, and then we do that. All right, that's what we're doing here also. All right, does it make sense to you, Vinta? All right, great. Now, in the sort by, we basically pass the function. Then second is a flag on the indicating whether sorting is ascending or descending, and then we are giving the number of partitions to create. Okay, so since sort by involves shuffling the data across the partitions, sort by, since it orders the data and sorts the data, so shuffles the data, therefore it also expects an argument called number of partitions, because it is more efficient to specify new partitions when the shuffling is anyway happening. So it takes a function that if you want, we can repartition while we are shuffling. It's like when we are moving houses, it's easier to change the rooms, right? It's easier to move things easily, move and decide which one goes where. So that's why number of partitions is required. All right. It's easier to rearrange things when we are moving houses. So in the same way, when we are sorting or shuffling operation is happening, most of the shuffling operations would have an argument, an optional argument, asking for the target partitions that we want. Okay. Does sort by returns a new RDD? Yes. Sort by gives you a new RDD. All right. So again, so
Sandeep, sort by the scalar function.
no, sort by is a function on an RDD. It's a transformation.
So it's a transformation given by Spark.
Yes, correct. Exactly like the way the previous function was. All the transformations are given, all the transformations, whatever functions actually we are talking are the functions from Spark.
Okay. It is inbuilt function.
Yes. So map partitions, map, flat map, these functions we are going to talk about are basically the functions from Spark. Great. All right. A question from Mohammed is, can you repeat the example? Example is, so sort by is going to shuffle the data. And that means that might involve multiple machines, multiple partitions, and so on. So sort by is going to move the data across the machines. And at this time, if you want different number of partitions in the output, this will be a good opportunity to specify the number of partitions, because if you are moving houses, it is good opportunity to rearrange things instead of first rearranging, then moving, and then rearranging, right? Or so it's better to utilize that opportunity of shuffling to create different set of partitions. Sorting is an exhaustive operation. Sorting is resource consuming operation. All right. So here's an example. So here we are creating a list which takes tuples just for the sake of it. So we have a list of containing tuples. These tuples have first value as string and second value as number. The first value as a character and second value as number. And here we are creating an RDD out of this TMP file. And then we are sorting it based on the first argument. We're sorting it based on the first argument. Okay. So we are saying that sort it based on the first argument. So here, yeah, this one is correct. The previous one was wrong.
So here it's taking the ASCII of the first element to decide the parameter routing.
Yes. Here is, oh, okay, sorry. I think you're right. I actually made a mistake. Yeah, you're right. Okay, so it is essentially sorting the data based on the first value here. So we are passing a function which gives, we are passing this sort by function. This is the function that it is taking. And this function, what it does is it gives the first parameters for sorting. And it gives you this list. Second one, in the second example, we are passing the second argument. We're converting this into second one, and then essentially the sorting is happening based on the second argument in this. Yeah.
Sandeep, what if there are repetitive values? Second argument, multiple tuples are
Um, Come again. So
so we
do you mean
are
to say that we want to say sort by both?
no, I mean to say like here we are sorting as part of the second value, right? If multiple tuples have same value like A1, B1.
Okay. Okay. So they will come in the same order, and that's kind of unpredictable in what order they will be.
Okay.
I think there's a function you sort by the second, and then if there's a clash, you again sort by the first.
Yeah, that will we call that as a secondary. You can sort by you basically you have to give a key based on that it can be sorted. All right. I'll show you. So when it comes to comparing objects or sorting, you can actually give out a tuple as well. So let me just see if we can give out a tuple.
Is it like we can call the same function twice once the sorting is done again on top of it? But
Uh,
that will be more resource
yeah,
cost.
that'll be yeah. So if you want to sort based on two elements, so you can do that. Okay. So let's say you want to sort by second argument, and then by the first argument. Okay. Let's see if it works or not. Okay. So it does. All right. So you can sort here. It's sorting based on the first argument, second argument first, and then the first argument.
Hmm.
So if we
Okay.
had, let me go back to your example. Let's say we had these elements here, like A, and then we have say 0 here, okay, and so on. So similarly, let's say we have for 1, we have B, right, as well as we have say capital A, right? So let's say this is our data, right? So this is our data A1, B2, 1, 3, D4. So this is character. First value is a character. Second value is a number. Okay. And when we are say sorting by the second, okay, let me just do it again. So this is our temp. Then we created an RDD. Then we're going to create an RDD. Where is that? Yeah, here. And then we are say sorting it. You can see. So it has A and capital A. So A is these all three ASCII values. I think it is taking them equal, and generally capital A is smaller than smaller A. Oh, I got it. So here the sorting is happening based on the first argument, right? Second argument first, which is 0, 1, 1, 1, 2, and then 3. So the sorting is happening on second argument first and then first argument. In the same way, if we swap these order, right? Can you mute? Okay. All right. So here you can see this time we have sorted based on first, then second. All right. First, then second, and you can see in these cases the ordering is correct now. All right. You want to give it a try? All right, I'll just give you the history. That is the smarter way. All right. And okay, I'll just start from here. This is good enough from here, right? Okay. So you might have to remove the history number. You can just, I can just do it for you. Or you can do it. All right. And bring it in the single line and then execute. All right. A question from Sachin is, I did not understand the ASCII value concept. So every character has a number associated with it internally. So when we put something in a single quote, it's essentially a number under the hood. It is essentially a number under the hood. So if you take a look at the ASCII values, okay, ASCII values, right? The reason here you can see capital A has come last. Okay, capital A has come last because its ASCII value is supposed to be the smallest. Okay, so its ASCII value is maybe the, okay, yeah, you can see capital A comes before small a, right? Capital A comes before small a is small b, and this one is a character here, not the number. When you put it in a single character like this, it is a number. Okay, it is a number. So the ASCII value of the ASCII value of these numbers, the character set. So you can see here, capital A, where is capital A? Capital A is 65, while small a is 97. So capital A is smaller than smaller a based on the ASCII value. All right. So every character under the hood is a number. It's just that the programming languages, while printing them, convert that number into a printable character, and that's how it works. All right. Single quote is a number under the hood, double quote is a number under the hood, and so on. Okay, so this is how it is. So every character is a number under the hood. A question from okay, a question from David is, how does it scale for 1 million entities? A good question. A good question. So yes. So if you have 1 million entries, what it's going to do is it's going to do first, it's going to use this function, whatever you are passing here, to generate the key for every element. And then the work of sorting will be distributed on multiple machines. Every machine will be computing the sorted order of their partitions. And once the sorting is done, then it will be merged and repartitioned in a newer fashion. Okay, so the sort by function is the core of Spark. It's one of the core algorithm that won the sorting benchmark, and because of which Spark is used worldwide. And it essentially does the sorting distributedly, the way we talked earlier, the way sorting happens in a distributed fashion earlier, that first each partition will be sorted individually, then all of these partitions after sorting will be merged to create the final output. All right, that shuffling operation is again distributed, and often we don't need to know that. We just need to control the order on which the sorting will happen. That we can control by the way of sort by function and passing our own function. All right, so a question from David is, can you do an example? All right. So yeah, so the way we discussed last time, okay, the way we discussed last time, let's say you have a partition 1, 2. So let's say, imagine that we have 3 machines, right? On first machine, it is 1 to, let's say 11, 2, and 10, correct? And on second machine, we have second partition, which is having, say, 3, 1, and 20, right? And third machine is having, say, 4 and 2. So first, this will be ordered on machine 1. This will happen on machine 1. Okay, this will be ordered on each machine. So this will become 2, 10, and 11. And here, this will become 1, 3, and 20. On this, it'll become 2 and 4. So this is happening, this work is happening on individual machines. Okay, on individual machine. Now, afterwards, these records will be shuffled, as in they will be from here. Let me make it a little more. Okay, then the shuffling will happen. We'll pick the smallest out of these and then put it in the output, the smallest one in the output. So we'll pick from here one, and that will go in the output direct output one. Then we'll again compare these, pick the smallest one. Okay, pick the smallest one, right? And then we again pick the smallest out of this. Okay, and we again pick it this smallest. So it's actually pretty smooth to
This is like similar to the merging of sorted list, right? I
yes,
mean,
yes, yes,
example.
yes. It's the same algorithm. So just that Spark does a bit of more optimizations in terms of appropriately moving only the elements where it's required. Okay, good. Thank you, clarifying, David. So this is what the usual sorting is. Question is, imagine that we have gigabyte or terabyte data, but how would the files be loaded, read, sorted, and the results be given? All right. So when we are doing this here, let's say we have an RDD, we have hundreds of operations before it. This this function, so this will happen only when you do collect. Okay, there could be multiple operations happening in between. So the loading of the files and everything would remain exactly the way we have learned. And the sorting could happen on any RDD, whether it's loaded from the memory, it's loaded from the file system, it's loaded in the HDFS. Okay, imagine that we are loading data from, imagine that we are loading data from HDFS. Okay, imagine that we are loading data from HDFS. You have a huge file that have these chunks, okay, that have these blocks. All right, like this. So imagine that we have this HDFS file, okay, where this is the block 1, this is the block 1, this is block 2, this is block 3. Okay, so right, and when we are creating say our RDD, let's say we are creating an RDD from this file, what will happen is it'll create the partitions equal to the number of blocks, something like this. Okay, something like this. So this RDD will have partitions generally similar to the number of blocks in the HDFS file. Let's say it is 3 blocks. Okay. So the RDD will basically map. It won't load the data. It will just map this with this. Okay. And then when we are running application, let's say this is our Spark application. All right. Let's say this is our Spark application, and then okay, and then we are basically executing sorting. Okay, so this will happen parallelly on so many machines. Okay. All right, and yeah. So a question is, can we do it on the data located on the cloud? Yes, definitely we could do that. So let's say we have our RDD. Let me see if I could give you a little bigger data. Let me just pick a data and then we'll decide. Okay, so let's say we have file, browser, and we go to the data, right? Okay, imagine that we have this Chicago crimes data. Okay, Chicago crimes data, right? And let's say we want to just sort it by line, just regular. This is already sorted by the record ID. Okay, and all right. So we could just, yeah, we could just write. Should I do it with this? It has 1.4 gig. Yeah, let's just pick the say the second argument here. Okay, to do that. All right, let's write it. Okay, who is going to help me with the writing? So this is my file. So this is the RDD I'm creating. So I'm saying sc.text file. Again, it's a text file. All right, and this is the data. This is the file that we are going to process. Okay, so this is the file that we are going to process here. It's a little too big a name. Okay, yeah, this is it. And this URL is wrong, so we'll have to specify URL like this. Okay, so we are saying sc.text file, and then we are saying rdd dot sort by, and we're defining a function here. Okay, and the function is going to be the f function, defining f, which takes a line which is a string, and it returns the key, right? It returns the key. All right, let me just show you what is it that we're talking about. We're talking about creating the function like this. So we can actually also just simply say whatever is the line. Okay, so we could say line and lines dot split based on the comma, and then return the second argument, right? If the line was this line, okay, the line was this line. Okay, so if let's say this was our line, if let's say this was our line, so what is it that we are trying to do? Oh, it has the double quote already.
Assignment is missing.
Yeah, no, it has the double quote already, so we will have to, yeah, assignment is also missing. All right, so this is our line, and let's say what we are saying is line dot split. It's split by comma. Okay, and then we are saying give me let's say this one. Okay, let's say this one, and right now let's just sort it based on just a string, not anything else. So 0 1 2. Okay, all right, so I think that will sort the data based on our third string. We could further convert it into time and things like that. Okay, so here we go. And then we say, all right. All right. So this is our result of sorting. And then we can either just take a look at few records, or we could save it in some file. Okay. So I'm removing this function. So this is the function for sorting humongous data. All right. Also, I'm going to, yeah. So right now, this one is running on one particular node, we'll have to convert it into multi-node one, okay, to make it really fast. Okay, right now if you see, I think it's essentially running everything on a single machine. We'll have to change it. Okay, so it has done the sorting. You can see this, you can see 0, 0, 0. So this one is come before the second record. Okay, so from here, okay, till probably here, right? So the data is now ordered based on this time. Okay. All right. To make it a little faster, what you have to do is you have to run Spark shell with saying master yarn. Okay. So, no, actually, it is to be dash dash master yarn. Okay. So all right. So I said Spark shell dash dash master equals yarn. It's trying to connect to the yarn and trying to launch the Spark shell. Okay. Master yarn means execute everything on the cluster. So there's something wrong here.
So just this command will distribute the work among all the available nodes, and
Yeah.
Jan will take care of the coordination.
Yes, yes.
Our setup is like a 5-node cluster, right? A 5-node cluster.
Right. So I'm just wondering what is happening here. It always works out of the missing operand topology script. I see. There is some topology script that we had created is causing the issue. Okay. All right. I'll take a look at this one. Probably the yarn mod is not working. So we'll have to take a look at it maybe tomorrow at some time, because this is supposed to work. Yeah, I'll just give you the code. So the important part here in this code is no matter how many machines you are having, whether you are running in uh, on right, whether you are running on Amazon, whether you are running on local cluster. So it is, this piece of code is actually doesn't care about underneath, right? So it's basically, that's the importance of it. Just like in databases, you don't need to worry about whether where is the data file and where are the records, doesn't matter whether it's in memory or not. In the same way, in case of Spark, this will take care of everything. All you need to define is what is it that you're looking for. Okay. So under the hood, everything else will be done by Spark for you. So all it'll do is load this as an RDD, and then it'll convert the records into break each line by comma, and then use the third column out of it as the criteria for sorting the data. Yeah.
So second means third column, 0, 1, 2.
Correct. Okay, that's right. So all right, let's take a break, and after the break we will continue from here. Great. So before the break, what we did was we did the sorting of plain text data based on a particular parameter. And we were successfully able to sort the data based on third column of a comma separated file. Although the way we used was very rudimentary, but there are similar sophisticated ways to load the data and split the data, even the data which has comma in it. For example, if you take a look at this data in this, here, the last element actually contains comma in it, right? So, okay. So we could do multiple things here. We could parse this, each record using a sophisticated CSV parser. We could, instead of just using the split, the way we used simply the split, the string-based operation for splitting the text, we could also use, say, a given CSV parser, some library which knows how to handle the complex CSV, and we could use that to parse this data. Similarly, what we could have done is here we could have also done a regular expression-based parsing. So it is up to us how do we want to tackle that. So there are multiple ways of doing the same thing, and each one has its own advantages and disadvantages. The one that we used was extremely simple one. We wanted to get the work done really quickly. So we basically splitted the data and ordered the data just based on this. Okay. Sometimes you may realize that, okay, this is not a good way, because if we first want to sort the data based on the year, then month, and then date. Okay, right now what will happen is first the data will be sorted based on this, then this, then this. So because that's how the strings are sorted. All right, so that's what we did before the break. Now, so we have already done this part. Okay, other than these basic functions, there are some set-like operations are also provided by RDD, such as join and union and so on. Though RDD is not really a set. What is a set? In the set theory, you must have read, the set is something, a collection of unique elements. Set is a collection of unique elements. So though RDD is not really a set, but the set operations try to provide you utility set functions that you can use. Okay, so we have RDD, and let's say you want to find the distinct element from an RDD. We can use an inbuilt function called distinct. Okay, we could use an inbuilt function called distinct. And if you want to say concatenate two RDDs, we can use union. If you want to subtract one from the another, let's say from RDD1, we want to subtract the RDD2. RDD1 is having coffee, panda, monkey, tea. And we want to subtract coffee, monkey, kitty. From this one, what will happen is coffee will be gone, both of them. Monkey will be gone. Sorry, monkey will not be gone because monkey will not be gone because monkey is different from money. Okay, and kitty will be gone. So here you are left with panda, monkey, and tea, though the answer is wrong. Okay, so you'll be left with panda, monkey, and tea. Panda, monkey, and tea, because here it's not money, it's monkey. Yeah, that's a typing mistake. All right, actually it was supposed to be monkey. I see now. Okay, 1K has gone missing, that's why. All right, now we could also do intersection. Okay, so what does intersection do? Intersection basically does the exactly the set intersection does. It finds the common values in RDD. It also removes the duplicates. Okay, so these are quite useful ones. So another one is Cartesian. Cartesian basically does the cross product. If you have certain elements in one RDD and you do the Cartesian against another one, you will get all of the combinations of the RDDs. Okay, so I could try showing you this. So imagine that we have where A equals list of say Sandeep and say okay, Alok, right? And here we have another list called B where we have Giri and say Tripathi. All right. So this is what we have, and what we can do is, and both of these are say RDDs. Okay, we say parallelize in both of them to convert it into an RDD of Spark. Okay, so this is what we have, and we say A Cartesian B. All right, let's see if it works. Let's say, does it work? All right. So we have A and B. We could say A Cartesian B. All right. It gives us another RDD called C. We could say C dot collect. All right. So you could see here, it has generated all combinations. Sandeep Tripathi, Alok Tripathi. So this is how it has done the all permutations of these. Okay, you could try the same thing.
Cartesian will give all the probability, all the permutations.
Permutations, that's correct. Okay, oh, this is the one which is for today. I'll just put it here. Okay, so let me just give you the history. Good. And should I start from here? Now, a question from Muhammad is, what are the applications of Cartesian? All right. So there are many applications of Cartesian. You'll be amazed to know that. Imagine that you are trying to join two data sets, right? And you're trying to join, say, the data set where okay, so let me just go back and explain. All right, so there are many applications. This basically with Cartesian, you can replicate the joins of databases. Okay, you can replicate the joins of databases. What is a join? Join or cross join in case of databases, it's a permutation of one table's rows against another one. And when we put a where clause, so if you follow a Cartesian follow by filter, you have created the equivalent of select star from A comma B where condition, right? Here, this is a condition, and this is where the joining is happening. Or let me just put it explicitly, join B, where A dot something is equal to. So this is basically, the utility is similar. Correct. It's a kind of a join. All right. No, actually, you can create non-equijoins also, whereby you can compare two things, greater than, equal to, and so on. All right, that was a question from Binta is, what are the advantages of RDD over data frame in part and regular? So, okay, there are multiple questions in a single chart. So one is, there is a data frame called Spark, right? In the Spark itself, there is a data frame. Now, data frame means RDD with columns, okay? RDD with columns. So then there is a library of data frames in Spark. So most of the structured data we will be processing with data frame, but unstructured data we must know how to prepare using RDD. It is really easy and quick to get used to processing the structured data. So I don't need to teach that part to any of you. You can actually learn it very quickly, although there is a chapter dedicated for that, because all of you, I'm assuming, are having some background in SQL. So you will be able to handle the data frame by yourself easily. I will definitely give you a kickstart. And then the RDD part is something little requires a bit of thinking through. Now, the next question is, how is it better than Python or Pandas data frame? Because Python and Pandas data frame is in the memory. So Spark's data frame is better than that. Now you know the difference between RDD and data frame. RDD is unstructured data, some data in which we don't know the columns, but we have a definition of the row. Okay, and similarly, regular SQL also. Regular SQL, Python, Pandas perform everything in a single machine. Okay. Regular SQL is better than Python and Pandas data frame because it tackles the data if the data is going beyond the memory size. Okay. So Python and Pandas is really fast, but it consumes the memory. So there are multiple. Yeah, I think. Okay, let me just. Yeah, it's a good idea actually just to put it in the slide. Okay. So first question, this question has multiple one. One is RDD versus Spark data frame. Okay, that's the first question. So RDD is for unstructured data, while data frame is for structured data, right? Now, next question is Spark data frame versus, say, Python data frame. Python or Python data frame, right? So Python data frame, or say Python/Pandas, right? So Pandas is in the memory, and Spark one is distributed. This one is distributed, and that one is in memory. Okay, and the regular SQL versus say Python. Okay. Okay, so this one is paged, and even if data is not fitting in the memory, it can still work. But this one is not paged in the memory. Okay, but this one is far more powerful as compared to that. So these are the quick way to keep in mind that. So regular SQL is little better than Pandas or Python when it comes to the memory issues, but regular one, this one is only, you can only do SQL, but here you could do far more powerful operations. Okay, so maybe what I could do is I could create a table in which on x-axis the columns are various things like RDD, pandas, etc., and rows are features. Let me just do a blog post on this. Probably that will make more sense, because there is always this confusion that which one to use. Okay. A question from Grishma is that MS SQL 2012. Yes, that's right. So all these databases actually support in memory also, but in memory is not great, and is though these are basically equivalently faster, but regular SQL is more, can handle more bigger tables than pandas. Okay. okay, can handle bigger tables than pandas. All right, so that was a very quick comparison. All right, so I was able to give you a quick example of the Cartesian. All right, now this is an interesting operation. So there is a function called fold, or you can call it action called fold. It is a little more it's a bit more sophisticated version of reduce. It's a cousin of reduce. There was a reduce function, right? A reduce action on the RDD that we used for computing sum, and in which the average was not working, right? So the reduce function basically was actually not very customizable or controllable, right? So fold provides a little extra control over the initialization. That's all. So what it does is it aggregates the elements of each partition, okay, and then results of all the partitions are aggregated together using the given function which you pass to the argument and a neutral 0 value. Imagine you have partition 1 and partition 2, and what you want to do is you want to sum it up, and you're passing an initial value as 1, sorry, some initial value, maybe 0 or whatever. So first, the first value will get merged into the initial value and every partition, then the rest of it, second and third, and that way, so these will merge here. Now you will have to define a function how to merge 1 into the result, 7 into this, 2 into this. Okay, so first we'll merge 1 to the initial value, then 7 to the initial value, then 2, and so on. And then once we are done with this, then we will define, then the same initial value will be used again to merge the results together. Okay, so it's like essentially the reduce, just that we have an extra thing called initial value into which things are getting merged, and you will have to write a function which knows how to merge initial value and individual value, or how to merge this kind of data type with this kind of value. Okay, so in most cases your reduce function will be perfectly fine. Only in certain functions this need might arise. Okay, all right, so let's say we want to concatenate everything to underscore. Okay, it's a very arbitrary example, doesn't look like very sensible thing to do. So first thing we did was we created a concat function. We are basically concatenating everything to underscore. Okay, so since we have created two partitions, 1 to 10, there are two partitions. First partition from 1 to 5 and second partition from 6 to 10. Now when we are concatenating the values here, what's happening is first partition will get merged into first underscore, then second partition will get merged, and then overall get merged, both of these strings, this string and this string, just like what we just defined here. So imagine that we are just concatenating instead of summing up, and the initial value is underscore here and here. So that's how the initial value plays the significance. Okay, so when you are designing an algorithm or when you are building a larger project, you might require such kind of function. Okay, so here the values are being concatenated to the initial value. Okay, so we have defined a function called concatenate, which takes two strings as argument, s and n, and we are appending the two. That's all. Okay. So, all right. Similar to a little bit more sophisticated version of the previous one, the fold, we have aggregate. Aggregate is far more sophisticated version. Aggregate is far more sophisticated version. And what aggregate does is it goes one more further. It lets you define two operations. It lets you define three things. First, initial value. Second, sequential operation. Third is combination operation. Okay. So when we are merging all the values of each partition, the sequential operation is called. When we are merging from the sequential operations, then the second function is called. This is again far more customizable version of the reduce. So you can create any kind of reduce function using aggregate, but not the vice versa. Okay. Similarly, you can create reduce using this, but not everything can be done with reduce, which it can do. I don't have example as such, honestly, for like something that fold can do, but reduce can't. So here, the aggregate is a little bit more sophisticated than fold. It lets you define two separate things. Earlier, the reduce function was doing both the things. Reduce function was called on while we were aggregating the values on the same partition, as well as while the values were aggregated across the partition. Then there were two different functions. So here, this aggregate function is basically a bit more customizable version of reduce. Okay, this diagram will make it more clear. Okay, so imagine that. Okay, let me just show you the second diagram that we created last time. Okay, let me just show you this diagram. Okay, so when we are aggregating, we are basically trying to combine all the records from all the whole RDD into a single value. Imagine that we had an RDD with these values like 10, 5, 1, 2, then and so on. We have 5, 8, 10, and 5, and so on. So the aggregation function, like the red one, will be called on every machine, while the resulting value will be called here. Okay, and let me see if I have a clear picture on this. All right, can I design this this way? Right. So yes. Okay. All right. I think I'll go ahead. Yeah, I'll describe to you again. So notice that in these cases we have an initial value. Okay, initial value, and this is your data from RDD. Notice the shape of these things. Imagine the shape represents the data type. So initial value is round and the RDD values are square. Okay, so first function that you write called sequence operation, it's going to take the square and combine it with the circle. Okay, that's what it's going to do. So whatever is the data type of this one, this function should take two arguments. First, same as the data type of the initial value, and second, same as the data type of the square. Then we need to define a second function, which takes the, so same function will be called again, this time with this and the second argument. And this way, this function that we are using to combine these values will be called parallelly on other partition. Okay, initial value will be initialized on both the partition parallelly. Imagine, so what is it that we are trying to do? We have an RDD of some elements, and what we want to do is we want to combine the values. And what we want is we want finer control over how our values on the same partition are getting concatenated and how our resulting values from every partition is getting concatenated. On top of it, what we want is we want a certain initial value to which these values will be concatenated. All right. So an example could be that initial value could be our, say, sum and counts tuple. Okay, this is our sum and counts tuple. And we are defining a function called sequential, which takes a tuple as argument. Remember this? This is a different data type. It's a tuple. And the second argument is an integer. This is the circle, and this is the square. Okay, so you are defining a function called sequential, which takes two arguments. One is circle, other is the square. It knows how to merge an integer into a tuple. Okay, and then we get these results. Okay, so basically here what we are trying to do is we are adding this value. So again, as larger program, what is it that we are trying to do? We want to compute the average, right? And for that, what we are doing is we are going to compute sum and the count, both of them, as we did earlier. Now, here what we want to do is we want to, instead of using normal reduce, we are making it a little more efficient by defining an initial value, which is a tuple. So all of the values, okay, all of the values. So David, you want me to explain this example again, the average one? Yeah, I'll explain again. This is the one example. Okay, so I will delete probably the drawing may be incomplete. So okay, instead I'll just draw it for you separately. This is better. Okay, so yes, let's just, yeah. So what is it that we are trying to do? We have say an RDD with some numbers, and we have defined, let's say there is an RDD with some numbers. Okay, this is one partition, and this is another partition. Okay, imagine that this contains 1, 2, and so on till something, and this one contains 4 and 5. All right, and we are trying to compute the average. So here, initially what we define is 0, 0. Okay, that's the initial value, 0, 0. This initial value is initialized on all the partition. This is partition 1. Okay, this is partition 1, and this is 2. Okay, now everywhere this is the initial value which is defined everywhere. Okay, so initially we are defining that function. Second, we are defining a sequential function. Sequence function, what it does is this function will be called when the values are going to be merged into this. Okay, which means the sequential function should take the first argument as something that is same as our same as the initial value. This is a tuple. This is a tuple containing two values. Now we want to merge a value into this. So what are we trying to do? Initial value was 0, 0, right? 0, 0, right? When we are going to merge 1 to it, we are going to change this to 1, 1, 1, right? Then when we are going to merge 2 to it, it'll become, the resulting will become when we are merging two to this, I think I'm really pathetic at drawing. Okay, so when we are merging this and this using the function, okay, so this will become, will increase the, okay, increase the values by 1. Okay, then we are going to merge this and this. So sum will be increased by 2. Okay, and count will increase by 1, right? Because one more number is being added to the sum and the count. Okay. Similarly, this side, a question from Vidya is, how do we know there are two partitions? We're just taking an example. Okay, we can just find from the RDD how many partitions are there. Now 5 is getting merged this side, so sum get increased by 5, and how many numbers added? 1 is added. Then we are, okay, then we are adding 4 and this, so 4 plus 5 is 9 and 2. A question from David is, are those are you numbers backwards? So actually it doesn't matter. It doesn't matter. Okay, this could be anything, and this value could be here. I could have drawn it here. Okay, so the ordering of things does not matter. That's the most important part out of the whole of it, right? So whatever operation we do, we must know that these operations should be commutative. The order should not matter. All right. So here, initial value, let's say 5 was before, 4 was later. The result should always be the same. Okay. So once we have done this, so we get a tuple from one partition, we get tuple from another partition. Now to merge two tuples, we need a different function, right? Because our function was taking first argument as tuple and second argument as the integer. All right, though the name is called SEQ, okay, name is called SEQ. So what we are doing is we are basically merging it. All right, we're basically merging it. In reality, what happens is this is generally this side. Okay, this is generally this side. Okay, let me just try to move it. Okay, and try merging it. The result is anyway going to be the same. All right, David. So first, let's say 4 will be merged. So 4 and will become 4, 1, and then 5, 2. So that's how it is going to be. Okay. So you can think of it this way. So it'll be 4, 1, and then from here till here. Let me just delete these. Okay. I hope this is clear. Is this what you wanted? What you were saying? So you'll always get the same answer no matter what you do. And so here you notice that while we were combining values to the initial value, our function was taking the two argument. First argument was of the type of the initial value, and the second argument was of the type of the RDD. Right? Now we have to finally merge these results, and this one is giving us two values, both of which are same as the initial value, same data type as initial value. Now this one should take two tuples. So we need to define the second function. And what second function does is it sums up this and this. So it'll become 3 plus 9, which is 12, and 2 plus 2 as 4. Okay, so all we did was we defined two functions. First one combines the value of each record in the RDD into a tuple, and second one combines two tuples. Okay, second one combines two tuples, and we are calling the all right. Then we are calling the aggregate. Also notice that here, when we call the init function here, it returns another function on which we are calling with sequence and comp. Okay, notice the syntax here. Okay, notice the syntax here. So when we call aggregate with the init value, it gives us another function which we are executing with these arguments. All right. So here the comb operation, the combination operation is adding two tuples, while sequential operation is adding individual value to the tuple. All right. So all right. And this is how it works. I'll just show you if you want to give it a try. Okay, so you can see it is giving us these values. Okay. Now we can further divide this. We could say D, and we could say D dot underscore 1, D dot underscore 2. Okay. And this one is little hacky because I'm not sure if this works. Okay. All right. So no, it doesn't. We'll have to convert that into a decimal number to compute the average. Okay, because this is an integer, this is an integer. If you divide one integer with another, you get this. All right. So what we learned was that we could use two, we could actually give the results which are different, which are, the output is different data type than the input. So this aggregate function is useful when, specifically useful when the output is of different data type than RDD. Right? If you remember, in reduce function, both arguments x and y were of the same data type as the elements of RDD, as well as it returned exactly same data type. All right. So if you have a little more sophisticated need than using RDD, you could explore aggregate. All right.
Sandeep, this t underscore 1 is a variable.
T dot underscore 1 is the first element of the tuple T.
Okay, it is defined like that.
Yeah, here you can see there is a T that we are passing in the argument. T is a tuple of integer comma integer, right?
Okay.
Okay, so here we are saying add this and this. Okay, that's what we're saying. T dot underscore 1, T dot underscore 1, this first value of the tuple with the I, and increase the second value by 1. Meaning increase the count by 1 and increase the total value by the value of the integer, right? Because that's how the sum is computed. So what we are trying to do is we are taking the initial value 0, 0, and we are computing sum in the count by the way of these two functions. First function merges the individual value into initial tuple, and while the second function merges two tuples. Okay. Should I move ahead? All right. Great. So there are other more quite useful functions such as countByValue. You can just do word count using this kind of action. Okay. So when you have to do frequency computation, just like the standard word count example on using Spark, you could do that. Simply say countByValue. The only downside of countByValue is it is an action, and therefore it will give you a local array, and hence if your data is really big, then it could overflow the memory. Sometimes you want to just extract the top elements, then you can use top n. then sometimes you may want to extract the ordered value based on something. So it's equivalent of take and ordered. Okay, so you could sort by and take. You can actually get the same results using sort by and take. You don't need much of this. Now, similar to map, we have foreach. What foreach does is, foreach is great when we don't want any return value. Let's say you just want to print each partition, or you want to save the data into database or file. You don't want a new RDD. When you don't want a new RDD, use for each instead of map. Use for each instead of map, right? The differences from map is when you use for each, you do not expect any results. For example, you want to save the data to the database. For each is an action, while map is a transformation, meaning for each returns immediately. So when you don't want anything in return, right, then you use for each. All right. So similar to map partition, we have the way we have map and map partition. Similarly, we have for each and for each partition. Right? So what for each partition does is applies this function f to each partition in the RDD. This is actually very useful function when you are saving data into a file system or anywhere where you need to open a connection before. Okay. So here this code looks like in the right. So you can see that. So imagine that we have. Okay. So let's say we are doing partition sum, and we want to just print the sum. We don't want to construct a new RDD. Then we can just call the for each partition. All right. So we're using for each partition. You could do many things. You could do many things. All right. So that's pretty much with respect to the normal basic RDD. I would like to carry on to the key value RDDs. A question from Alok is it possible to do transformation of two RDDs in a single chain of transformation? I mean, cross RDD operation. Is it possible? Yes, it is possible. You could join them, union them, into the intersection, and then afterwards you could execute. All right. Great. So let's start with the key value RDD. Let me share the slides. Yes. Okay. Let me just share the slides with all of you. No, not hard. All right. Great. So we learned the basics of RDD. Now let's move on to a little bit more complex RDDs. So although we have already touched them, essentially key value RDDs are nothing but RDDs where each value is a tuple. Just that Spark detects that part that you have converted a key value into tuple, and then it starts providing you extra functions. So like RDD contains elements, and these elements are grouped into partitions, or you can say RDD is split into partitions. Node 1 might contain one part of the partition, node 2 might contain another part. Now, each individual value in an RDD could be anything. In the same way, it could be a tuple. Just note that the individual value is non-divisible. It cannot happen that half of the partition is in node 1 and half of the partition is another node in node 2. So that is not possible. And you can keep any kind of data in the RDD. Having tuple is quite useful because it is key value kind of model. So you could do joins, you can do group by, and so on. So data frame is definitely useful where you have clear definition of columns, but key value is also quite useful. Okay. Now, So a pair is defined at X, Y, Z. It's also called tuple. Tuples are immutable sequence of objects. You can convert a list into a tuple and you can define a tuple by yourself. Okay, so here is an example of RDD. This is an input data. It's a list of tuples. You can see these tuples are local. This is a local array. It's a local array. Then we are converting into a key value RDD using sc.parallelize. Okay. Now, so on tuples, since there is a key, the first element of a tuple is considered as a key. First element of the tuple is considered as a key, and therefore you could do many kind of operations like union operation, group by, joining, and so on, right? So the first such operation is reduce by key. Using reduce by key, you could group the elements and then combine the values of the groups using the function. So this is equivalent of MapReduce, okay? The Hadoop's MapReduce. So reduce by key groups the elements of an RDD based on the key and then reduces the values for each key using the function provided as argument. Let's take a look at this one. So here there are three values for the key 1, 2, 3, and 6. And for the key called 2, we have only one value called 4. So here we are saying reduce by key, and basically it's going to group the data based on the key. Okay, it's going to group the data based on the key, and then all the values are combined like this. Okay, all the values are combined using this reduce function. So first, let me just show you this part. And okay, you can see it has combined all the values using the provided function. Okay, so what's going on under the hood? When we are saying the function that we passed was just sum, a plus b, that's all we passed as argument. So first of all, it grouped the data. It grouped the data based on the key. By default, the first element of each tuple is the key. And so the first element is basically the key, and these are the various values. Okay, a question from Mohammed is, isn't it very hard to remember so many transformations? Actually, yes. So what you do is you remember the basic ones. You know what it means by map, flat map, and reduce. Okay, and then using those, you could actually get rest of things done. Okay, so it might take a bit of practice. Similarly, reduce by key is something that you would require multiple times, and so you can't forget these. Sort by you can't forget. Okay, so great. Now once this is done, then you are combining multiple values using the same reduce function. Okay, so just like we have reduce by key. Just like we have map values, map keys. Okay, so you won't forget that way. So all right, now using this knowledge called reduce by key, we can revisit our word frequencies example. Now it will make more sense. Imagine you have a huge text file, and you are trying to compute the frequencies of all of the words found in the file. Frequencies meaning how many times each word is repeated, right? All right. Or in other words, to find the unique words in the text and find how many times each word has occurred. Okay. So imagine that you have a text file containing 2 lines, sa, re, saga. Why I have used these single syllable things? Because that saves the space on the slides. And we want to compute the word frequencies. Like ga has occurred once, re has occurred 2, and sa has occurred twice. Right. So how would we solve this using the knowledge so far we have gained? So we load the data. We load the, first of all, in the first go, we create an RDD out of the text file. Then using the flat map, we are converting each line. This basically, this RDD has 1 line per record. This RDD has records. Each record corresponds to 1 line from this file. That's what sc.txt file does. And then against every line, we are calling flat map. Okay, and what flat map does is it converts 1 record into multiple. So our function is converting 1 line into an array of words. 1 line into array of words. Therefore, flat map would gather all the words and will create a new RDD having 1 word per record. Lines had 1 line per record. Here, words has 1 record per one word per record. Okay.
Here, space will also be considered as a word, right? Because
Which one?
a space. So at the end of the line, you have spaces, right?
New line.
No, so the split between 2 words is space, but at
Yes.
the end of the line, you have a lot of spacing. So
A
when
new
that
line.
will be considered a new line, correct?
Yeah. So basically the way, if you look at the file, the way the file is generally like this. Okay. File is generally like this. So there is 1 character in the beginning. Then there is space. I'm putting /n / space, or I'll just put some special character here. I'll just draw something. So let's say there is 1 line containing sa, and then is a space. I'll put like this. This is then ray. This is a space, and then again another space, and then there is a new line character. Okay,
Yeah.
this is a new line character. It's a single character, and then again a word, right? And then it continues. So you can think of the whole text file as a single string of characters. It has some of the characters as spaces, some of the characters are these special characters called /n. Okay, that's what it means by a text file. All right.
All right, got it.
Okay, great. Now the first thing we did was we used flat map to convert lines into words. Okay, so this became this. Is it clear? Sa, re, that was first line. Saga was second line. It became a single. If the RDD is vertically drawn, this will be first record, this is second record, and this third record, and so on, right? So I hope this is clear to everyone. And next is we convert these into pairs so that we can apply our reduceByKey, because reduceByKey takes the key value pairs where the key is something on which we want to group the data. So all we are trying to do is we want to group the words and then compute the counts. Okay, so at this point of time, once we have created these pairs, right? We have created these pairs. We could actually use the countValues function and get the results, right? But that's an action, and it will bring all the data to you. Finally, when we say pairs the reduceByKey, it's going to group the data first, like this. And where the values are whatever you have put in here we have put numeric 1, you could put X, Y, Z or whatever. And then it reduces it into something like this. Okay. Okay, so basically, reduceByKey is a combination of group by and aggregation. It's grouping by and aggregation. So aggregation is you passing the aggregation function as argument. Aggregation function as in something that aggregates multiple values, not the Spark's aggregation. So we are passing the aggregate function as argument, and we are calling it on our key. So it's grouping the data by the key and aggregating all the values for each key using this function. All right. This is basically the reduceByKey is going to be very useful, right? Because you can actually emulate a lot of things using the group by.
So it is key is GARA.
Yeah, this is a key. This is a key, this is a key, this is a key, and the values are just numeric. We have just filled in the values by ourselves.
So groups will delete the duplicates.
Group will not only delete, they will bring them together.
Okay.
See, Ray has become together. All right.
And reduce will sum up.
Reduce will sum up.
Yeah.
Okay. So reduceByKey does both the things, grouping and reducing. reduceByKey groups the data and reduces the groups. Okay.
This is just like SQL group by, right?
Correct. The only difference is in SQL, you can only call the functions defined in the SQL as an aggregate function, AVG or SUM, count. Here, you can define your own aggregate function. Yeah, that's far more sophisticated, right? Similar functions were there in other similar competitive products like Pig. There, you couldn't define your own aggregate function so quickly, and therefore it wasn't very useful. Here, even when you are processing unstructured data, you could actually do a lot of sophisticated works by utilizing the local languages, the language which you're using, by utilizing the functionalities provided by that. Like, okay, a question from Raju is, here both A and B are the values of a specific key? Yes, I think this diagram will make more sense to you. I'll just show you this this one. So when we were doing reduceByKey, first it groups the data like this. So this is the key and all the values of it are grouped together. And then we are reducing all the keys of each group. All right. Does it make sense, Raju? Okay, great. All right, so this is what's happening. So you can see that the word count example is actually very, very simple. Also notice that we have just used s.lowercase. This is a function provided by Scalar. Okay, so we can switch back and forth and use any function Scalar as part of Spark. Okay, which was not possible. Let's say you're using SQL, you can't really use any other programming language so quickly unless something is provided as part of the SQL. Here, the work is being done by the Spark, but code, the functions, the libraries, anything could be done here. Imagine, now let me just give you another example. Imagine that data was a lot of email addresses from people. Okay, lot of email address, like 1 million email address, and you had to distributedly send 1 million emails using many machines. So you could just do flat map, get the all emails and email.map, and here you could write Java mails code that send the email to this person. So that work will be distributed. Similarly, let's say you are having a file in which there are millions and billions of URLs, and you want to write a function which could download all these URLs using, say, 500 machines in your network. So all you need to do is load that file containing the URLs, do the map. Inside the map here, you call your function that's going to download the data for that URL. And that way, that download data could be in Java or could be in Scala. We could actually call that function. So that's the magic about using this kind of terminologies. All right. So using this kind of mechanism. So RDD is very sophisticated because we could do anything we wanted. Downloading data, sending emails, applying regular expressions, doing whatever is possible using programming, we could almost do that. A question from Hiten: words, pairs, and counts are just variables. Yes. So words is an RDD, pairs is an RDD, and counts is the local value, because reduceByKey is an action. All right. No, reduceByKey is a transformation. ReduceByKey is a transformation. When we say count.take, then it brings it local, and when we say counts.save file, then it saves in the database. Let's just call this. All right. So I'm going to take one more example of reduceByKey because that's actually very useful function. What is the command to take last 10 records? Okay, a good question. I doubt if they have a command to give you the last 10 records. Okay. Okay. So
I
do
think
they
it's
have
-10.
it is there?
I think it's -10 or it's tail.
Okay, let me just see. I have not used it yet. So let's say we have out, which has two tuples. If I say out.take and say -1, will it give you 2, 4? No. And if I say 1, it gives me in the beginning. All right. No. All right. I doubt if they have tail. Do they have tail? I've not. No. Okay. Yeah. One more thing I wanted to discuss earlier, which is not yet discussed. Okay. So you may want to do this. Okay. Yeah. So you can get the number of results using count. Okay. This is something I wanted to discuss earlier also, and I keep missing it. Okay. Great. Now is the time to discuss this part as well. So zip with index is something that is useful. Let's say we have an RDD, okay, and we want to put the index on every element of it. So you can always call any RDD with something called zip, or let me just say, let's say we have an RDD equals sc dot parallelize, okay, and we have, say, A, B, and C. Okay, A, B, and C. All right. What mistake did I do? Okay. So we have an RDD that has these three elements. What I want to do is I want to put indexes with it. Okay. Whenever we want to deal with, say, zip with index. Okay. So it'll create another RDD. Okay. Now we have another RDD. If you take a look at this, where we have put the indexes along with RDD 0, 1, 2, correct? Okay. Now on this one, we can sort the data. Based on the index. Okay, sort by, and we could say underscore dot underscore 2. All right, and say give me first record, right? Give me first record. So what it'll give you? It'll give you C2. Okay, we are saying sort by second one, and we are saying ascending equals false. So you can see it gave us the last record. So this way you could emulate the tail using this kind of method. Okay, so this way you could emulate the tail. All right. So what I did was I created an RDD like this. Okay, and then I zipped it with the index, meaning I put 0, 1, 2, 3 along with the value, converted it into key value, and then I collected it. Then just to demonstrate, and then I sorted the data based on the index, and I ordered it in increasing, okay, decreasing instead of increasing, and just took one element. I think that's how you will make a tail command. All right. The count of the records, you could always say RDD1 dot count. Is that what you're looking for? All right. Okay, word count. Okay. So the last one, the counts, we could just print. Okay. All right. Okay. So, okay, let me just go back to, I think I'm missing a very good point here. Let me try to understand. Okay. So here is, we are doing the lines, then doing words, then pairs, and then we are doing the counts, right? So this one will give us the counts. Now, your question is, this one will give us the counts. Either we could, now further, let's say here at this point, we want to find out which word is the most popular. We could just do counts dot sort by and so on. Okay, let me just show you this. And all right, so this is the counts. Okay, counts is right now another RDD. Okay, so here we could just take a look at this, or we could save it in the database. Okay, so here we have this key value pair containing the frequencies. Reunion has occurred 4 times, bone has occurred 361 times, and so on. But the data is dirty because right now you can see comma in the values. Okay, so a question from David is that how would I know how many words are there? Good question. So that you can simply say words dot count. Okay, words dot count. So these many words are there in total. All right. So this way you could actually do that. All right. So words dot count, pairs dot count. So you can actually count anything inside the RDD. All right. So here you can see these are the words. Now I wanted to say something cool. I think time is up. So we'll continue from here. So let's say we wanted to find out which one is the most popular word. So we could say ascending equal, sorry, we could just say false here and say, give me 10 records. So these are the most popular 10 words. Okay, the has occurred these many times. Empty string has occurred these many times. Off has occurred these many times, and so on. All right. So using this is something that required like two separate jobs in Hadoop MapReduce, and here you could do really quick. So basically, we could order the data and get the most frequent word like this. All right. So if you want to just extract, say, top 50 words, you could say like this. All right. Great. I look forward to see you all tomorrow. And thank you. Have a great day. So we'll continue from the temperature, the next problem of temperature. Okay. So yes. Thank you, Alvin. Thank you, Alok. Thank you, Bharti Raja. Thank you, Bintao, David, Grisma. Thank you, Raju. I'm happy that you found it great. Thank you, David. Thank you, Grisma, Hitendra, Jay, Mohammed, Rajan, Raju, Ravi, Sachin, Shravanti, and Subbu. I look forward to see you tomorrow. Bye-bye. Have a good day.